As you sit there watching this video, I want you to try something. Hold your hand up in front of your face. Look at it. Feel it. It feels solid, right? You can feel the weight of your fingers, the warmth of your skin, the firmness of your bones underneath. Everything about your hand tells you that it is a real, solid, physical thing. And yet, what if I told you that your hand, the hand you are looking at right now, is almost entirely made of nothing? Not mostly something with a little bit of nothing mixed in. No. Your hand is 99.99999% empty space. That is not a metaphor. That is not an exaggeration. That is a measured, verified scientific fact. If you could somehow remove all the empty space from every atom in your body, all 7 billion atoms that make you who you are, the remaining matter, the actual physical stuff, would be so small that you would need a powerful microscope to see it. We are talking about something smaller than a grain of sand. Actually, let me make this even more dramatic. If you removed all the empty space from every atom of every human being on Earth, all 8 billion of us, every man, woman and child, all the muscle, all the bone, all the blood, everything, the remaining matter would fit inside a space smaller than a single sugar cube. 8 billion people. One sugar cube. That is how empty you are. That is how empty we all are. And here is what makes this genuinely terrifying. It is not just you. It is not just humanity. It is the entire universe. Everything you see when you look up at the night sky, every star, every planet, every galaxy, every nebula, all of it is overwhelmingly, dominantly, almost exclusively made of nothing. The universe is not a place filled with stuff that has some gaps between it. The universe is a vast, almost incomprehensible ocean of emptiness that has a tiny amount of stuff sprinkled through it. And that tiny amount of stuff is itself mostly empty. It is emptiness all the way down. But here is where this gets truly strange, truly fascinating, and truly terrifying all at the same time. Because when physicists looked closely at this nothing, when they examined the empty space inside atoms, between stars, between galaxies, they discovered something that nobody expected. The nothing is not nothing. The emptiness is not empty. There is something happening in the void, something active, something dynamic, something almost alive. And what they found there has shaken our understanding of reality to its very core. In today's video, we are going to take a journey into nothingness. We are going to explore the emptiness at the heart of atoms, the void between stars, the terrifying gaps between galaxies, and the strange quantum world where empty space seethes with invisible activity. We are going to discover why 95% of the universe is made of things we cannot see and do not understand. We are going to confront the fact that even our own solidity, the feeling of being real and physical and substantial, is an illusion created by forces operating in empty space. And we are going to face the ultimate terrifying conclusion that the universe appears to be heading toward a state of maximum nothingness, a cold, dark, eternal void from which nothing will ever emerge again. This is going to be deep. This is going to be intense. This is going to change how you think about reality. So if you are the kind of person who loves having your mind completely blown by science, do me a favor right now. Hit that like button because it helps more curious minds find this video. Subscribe to the channel if you have not already because we go this deep on every single video. And leave a comment telling me, before you watch the rest of this, do you believe that true nothingness can actually exist? I want to know what you think before we dive in, and trust me, your answer might change by the time we reach the end. Now, let me take you back to the year 1911. The place is the University of Manchester in England. A physicist named Ernest Rutherford has given two of his students, Hans Geiger and Ernest Marsden, a seemingly simple experiment to perform. The setup is straightforward. They have a thin sheet of gold foil, incredibly thin, only a few hundred atoms thick, and they have a source of alpha particles, which are essentially small, dense, positively charged projectiles fired from radioactive material. The experiment is this. Fire the alpha particles at the gold foil and see what happens. Where do they go? How do they scatter? At this time, the dominant model of the atom was the plum pudding model proposed by J.J. Thomson. In this model, an atom was imagined as a uniform sphere of positive charge with tiny electrons embedded throughout it, like raisins in a pudding. If this model was correct, then the alpha particles should pass through the gold foil with only slight deflections. The positive charge was thought to be spread evenly throughout the atom, so there would be no concentrated areas to cause major deflections. And indeed, most of the alpha particles did exactly what was expected. They passed straight through the gold foil as if it was not even there. But then, something happened that nobody predicted. Something that changed physics forever. A tiny fraction of the alpha particles, roughly 1 in 8,000, did not pass through. They bounced back. They came back toward the source, deflected at angles greater than 90 degrees. Some of them came almost straight back. Rutherford later described his reaction to this result with a famous statement. He said it was as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. Think about that. They were firing particles at solid gold. Gold, one of the densest materials we know. And almost everything passed straight through it. The gold, for all intents and purposes, was not there. It was transparent to these particles. But occasionally, very rarely, something inside the gold was dense enough and concentrated enough to bounce the particles straight back. Rutherford spent weeks analyzing the data, and when he finally worked out what was happening, he realized that the plum pudding model was completely wrong. The atom was not a uniform sphere of charge. Instead, almost all of the mass and all of the positive charge was concentrated in an incredibly tiny point at the center, a nucleus. And the rest of the atom, the vast majority of its volume, was empty. Completely, utterly empty. He published his results in the Philosophical Magazine in 1911, and the world of physics was never the same. The atom, the fundamental building block of all matter, the thing that makes up everything you can see and touch, was revealed to be almost entirely nothing. Let me put this emptiness into perspective for you, because the numbers are hard to grasp with our everyday intuition. The nucleus of an atom is about 1 femtometer across. That is 10 to the power of negative 15 meters. The atom itself, measured out to where the electrons are found, is about 1 angstrom across, which is 10 to the power of negative 10 meters. That means the atom is about 100,000 times larger than its nucleus. 100,000 times. Now think about what that means in 3 dimensions. In volume. The volume of a sphere scales with the cube of the radius. So if the atom is 100,000 times wider than the nucleus, then the atom's volume is 100,000 cubed times larger than the nucleus. That is 10 to the power of 15. 1 million billion. The nucleus occupies roughly 1 trillionth of the atom's total volume. Let me give you an analogy that might help. If the nucleus of a hydrogen atom were the size of a marble, say about 1 centimeter across, then the atom itself would be a sphere about 1 kilometer in diameter. A full kilometer. That is larger than most sports stadiums. Imagine a tiny marble sitting at the exact center of a sphere that stretches 0.5 kilometer in every direction. Between that marble and the outer edge, there is nothing. No matter. No substance. Just empty space. And a single electron, smaller than the marble, somewhere out near that outer edge. That is what an atom looks like. That is what you are made of. Trillions upon trillions of these mostly empty structures, stacked together, giving the illusion of solidity. And here is what makes this even more mind-bending. This is not unique to hydrogen or to light elements. Every atom in the periodic table has this same basic structure. Whether it is carbon in your DNA, iron in your blood, calcium in your bones, or oxygen in the air you breathe, every single atom is this same vast emptiness with a tiny concentrated point of matter at its center. Heavier atoms have larger nuclei, yes, and more electrons, but the ratio stays essentially the same. The emptiness is universal. You might be thinking, okay, atoms are mostly empty space. But I am made of atoms, and I feel solid, so something must be different about how they are arranged, right? Something must fill in the gaps when atoms come together. But no, that is not what happens. When atoms come together to form molecules, when molecules come together to form cells, when cells come together to form your body, the emptiness does not go away. It accumulates. Your body contains roughly 7 billion atoms, and every single one of them is 99.9999999% empty. The reason you feel solid, the reason you do not fall through the floor, the reason your hand does not pass through your desk, has nothing to do with solid matter touching solid matter. It has everything to do with forces, invisible forces operating in the void. And understanding those forces takes us into the strange and wonderful world of quantum mechanics. Here is the truth that will change how you think about touching things forever. You have never touched anything. Not once in your entire life. When you think you are touching something, what is actually happening is this. The electron clouds of the atoms in your skin are getting close to the electron clouds of the atoms in whatever you think you are touching. And when these electron clouds get close, they repel each other. The electromagnetic force pushes them apart. This repulsion is what you interpret as the feeling of touching a solid object. But the atoms never actually make contact. There is always a gap, always a space between the closest atoms of your finger and the closest atoms of the table. You are floating above everything you think you are sitting on, suspended by electromagnetic force, separated from the world by an infinitesimal but real gap of empty space. But it goes even deeper than electromagnetic repulsion. The real reason you cannot pass through solid objects comes from one of the most fundamental rules in quantum mechanics. It is called the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. This principle states that no two fermions, which includes electrons, protons, and neutrons, can occupy the same quantum state simultaneously. What this means in practice is that when two atoms get close together, their electrons cannot overlap into the same states. They are forbidden from doing so by this fundamental quantum rule. This creates what is called degeneracy pressure, a quantum mechanical resistance to compression that has nothing to do with atoms being solid and everything to do with the mathematics of quantum states. So the solidity you feel, the resistance you encounter when you push against something, is not matter pushing against matter. It is a quantum mechanical rule saying that the mathematics of the universe does not allow certain configurations. You are held up by math. You are kept solid by equations. The emptiness inside you and inside everything you touch is real. The solidity is the illusion. Now I want to take you deeper. We have established that atoms are mostly empty space. But what about that empty space itself? What is in there? in the void between the nucleus and the electrons. Classical physics would say nothing. It is just empty space. A vacuum. But quantum physics tells a very different and much stranger story. And to understand this story, we need to talk about one of the most important principles in all of quantum mechanics, the Heisenberg uncertainty principle. In 1927, Werner Heisenberg formulated a principle that placed a fundamental limit on what can be known about a physical system. Most people know the uncertainty principle in terms of position and momentum. You cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. But there is another form of the uncertainty principle that is even more relevant to our discussion of nothingness. It involves energy and time. The energy-time uncertainty principle states that the uncertainty in the energy of a system multiplied by the uncertainty in the time interval must be greater than or equal to a very small but non-zero number. Specifically, the reduced Planck constant divided by 2. What does this mean for empty space? It means that truly empty space, space with exactly zero energy, cannot exist. Let me explain why. If space had exactly zero energy, then we would know the energy with perfect precision. The uncertainty in energy would be zero. But the uncertainty principle says that the product of energy uncertainty and time uncertainty must be greater than a certain minimum. If energy uncertainty is zero, then time uncertainty would have to be infinite, which is nonsensical in context. The universe does not allow perfectly zero energy to exist in any region of space for any finite amount of time. This sounds abstract, but its consequences are astounding. Because energy cannot be exactly zero in any region of space, even for a moment, the vacuum must fluctuate. Energy must spontaneously appear and disappear, so long as it does so quickly enough and in small enough amounts that it does not violate the uncertainty principle. Borrow a tiny amount of energy and you can keep it for a relatively long time. Borrow a large amount and you must return it almost instantly. This means that the vacuum, the empty space all around you and inside you, is not quiet. It is not still. It is seething with activity. Energy is constantly fluctuating, appearing, disappearing. And because of Einstein's famous equation relating energy and mass, these energy fluctuations manifest as particles. Pairs of particles, matter and antimatter, popping into existence from nothing and then annihilating each other and vanishing back into the void, all within unimaginably short timescales. These are called virtual particles, and they are happening everywhere, all the time, in every cubic centimeter of space, including the space inside your body, inside every atom, inside the space between your eyes and this screen. Right now, as you watch this video, the empty space in front of you is fizzing with virtual electrons and positrons, virtual quarks and antiquarks, virtual photons and gluons, appearing and disappearing billions upon billions of times per second. You cannot see them, you cannot feel them directly. They exist for such inconceivably short times that individual detection is essentially impossible. But they are real. We know they are real because they have measurable effects on the physical world. And the proof of this brings us to one of the most beautiful experiments in modern physics. In 1948, a Dutch physicist named Hendrik Casimir made a prediction. He said that if you take two perfectly flat, uncharged metallic plates and place them very close together in a vacuum, with nothing between them, with no force that should push or pull them, they will nonetheless experience a force. They will be attracted to each other, pushed together by nothing. This sounds impossible. Two neutral objects in a vacuum should just sit there. There is no charge to create electrostatic attraction. There is no mass difference to create gravitational effects worth measuring. There is nothing between those plates. Or is there? Casimir's reasoning was based on the quantum vacuum fluctuations we just discussed. In the open space outside the plates, virtual particles of all wavelengths can exist. Any wavelength is possible. But between the plates, there is a constraint. Only virtual particles whose wavelengths fit between the plates can exist there. Think of it like waves on a guitar string. The string can vibrate at many frequencies, but it can only sustain waves whose wavelengths fit neatly between the two fixed endpoints. Similarly, the space between the Casimir plates can only support a limited set of vacuum fluctuations. This means there are fewer vacuum fluctuations between the plates than outside the plates. More fluctuations outside means more radiation pressure from outside. The imbalance in radiation pressure pushes the plates together. The nothing on the outside pushes harder than the nothing on the inside. And in 1997, physicist Steve Lamoureux at Yale University measured this force directly. He confirmed that Casimir's prediction was correct. Two uncharged plates in a vacuum really are pushed together by nothing. Or more precisely, by the difference in the quantum activity of nothing on either side. Let that sink in. We have experimentally proven that empty space has physical properties, that nothingness can exert force, that the vacuum is not empty. The nothing between those plates is measurably different from the nothing outside them. This is not philosophy. This is measured physics. And there is another piece of evidence that is just as compelling. In 1947, Willis Lamb performed experiments on the hydrogen atom and discovered something strange. The energy levels of hydrogen's electron were slightly different from what the best theory of the time, Paul Dirac's equation, predicted. The electron in a hydrogen atom exists in specific energy states. And Dirac's equation told us exactly what those energies should be. But Lamb's measurements showed tiny deviations. The electron's energy was shifted slightly from the predicted value. This is called the Lamb shift. And when physicists investigated what was causing it, they discovered that the electron in a hydrogen atom is not alone. It is constantly interacting with the virtual particles that pop in and out of existence in the empty space around it. Virtual photons, virtual electron-positron pairs, all of them nudge the real electron slightly, changing its energy by a tiny but measurable amount. The empty space around the electron is not empty. It is filled with quantum activity that physically affects the electron's behavior. This was a triumph for the theory of quantum electrodynamics, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. They showed that you can calculate the Lamb shift by accounting for all the virtual particle interactions, and the calculation matches the experiment to extraordinary precision. The nothing around atoms is not nothing. It is a dynamic, active environment that influences everything within it. Now here is where things get really wild, and where one of the biggest mysteries in all of physics emerges. If the vacuum has energy, if empty space is filled with these fluctuations, then we should be able to calculate how much energy is in the vacuum. And physicists did calculate it. Using quantum field theory, you can add up all the contributions from all the virtual particles of all possible energies, and you get a prediction for the vacuum energy density. The number you get is approximately 10 to the power of 93 grams per cubic centimeter. That is an inconceivably large number. Now, we also have a way to measure the actual vacuum energy of space. The expansion of the universe is accelerating, and this acceleration tells us there must be energy in empty space pushing things apart. From observations of the cosmic expansion, we can measure this vacuum energy. The measured value is approximately 10 to the power of negative 29 grams per cubic centimeter. Compare those two numbers. The theoretical prediction, 10 to the 93. The measured value, 10 to the negative 29. The difference between them is a factor of 10 to the 122. That is 10 followed by 122 zeros. This is the largest discrepancy between theory and observation in the entire history of science. It has been called the worst prediction in all of physics. It is called the cosmological constant problem, and nobody, not a single physicist on Earth, has been able to explain why this discrepancy exists. We know the vacuum has energy. We can measure it. But our best theory predicts a value that is 10 to the 120, 2 times too large. Something is catastrophically wrong with our understanding of nothing. Either our theory of quantum fields is missing something fundamental, or our understanding of gravity and space-time is incomplete, or both. This is not a minor discrepancy that might be explained by a small correction. This is a chasm of ignorance that exposes how little we truly understand about the nature of empty space. Let me take you now to the edge of a black hole, where the nature of nothing becomes even more dramatic. In 1974, Stephen Hawking published a paper in the journal Nature that shocked the physics community. He showed, through theoretical calculation, that black holes are not truly black. They radiate. They emit particles. They slowly evaporate. And the mechanism by which they do this involves the quantum vacuum in a spectacular way. Remember those virtual particle pairs we discussed? The ones constantly popping in and out of existence everywhere in the vacuum? Normally, a particle and its antiparticle appear together, exist for an unimaginably brief time, and then annihilate each other, returning their borrowed energy to the vacuum. They come from nothing and return to nothing. But near the event horizon of a black hole, something extraordinary can happen. A virtual pair can appear right at the boundary of the black hole, and before the pair can annihilate, one particle falls past the event horizon into the black hole, while the other escapes into the surrounding space. The escaping particle becomes real. It is no longer virtual. It has become an actual detectable particle radiating away from the black hole. And the energy for this particle has to come from somewhere. It comes from the black hole itself, which loses a tiny amount of mass in the process. Over immense timescales, unimaginably long periods, this process causes the black hole to shrink, to lose mass, to evaporate. Given enough time, even the most massive black hole in the universe will evaporate completely, leaving behind nothing but a faint bath of radiation. Empty space, through quantum fluctuations, slowly destroys black holes. The nothing eats the something. The void consumes the most powerful objects in the universe. It just does it very, very slowly. Now, I want to shift our perspective outward. Far outward. We have talked about the emptiness inside atoms. But what about the emptiness between things? Between stars? Between galaxies? What does the large-scale emptiness of the universe look like? Let us start with our own cosmic neighborhood. The nearest star to our Sun is Proxima Centauri, at a distance of about 4.24 light-years. That means light, traveling at 300,000 kilometers per second, takes over 4 years to make the journey. If you shrunk the Sun to the size of a grain of sand, about 1 millimeter across, then on that same scale, Proxima Centauri would be another grain of sand about 6 kilometers away. 6 kilometers of nothing between 2 grains of sand. That is how empty our local space is. And the nearest star is close compared to the distances within our galaxy. The Milky Way is about 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars. That sounds like a lot. But spread them across a disk 100,000 light-years wide, and the average distance between stars is about 5 light-years. Each star is a tiny island of matter surrounded by an ocean of void. If you were placed at a random point within our galaxy's interstellar space, what would you find around you? Almost nothing. The interstellar medium, the material between stars, has a density of roughly 1 atom per cubic centimeter. Compare that to the air you are breathing right now, which has approximately 25 billion molecules per cubic centimeter. Interstellar space is roughly 10 to the 19th times emptier than the air in your lungs. And even that seemingly empty air is itself mostly empty, since the atoms that make it up are themselves mostly void. Emptiness within emptiness within emptiness. But the interstellar medium, sparse as it is absolutely crowded compared to what lies between galaxies. The distance to the nearest major galaxy, Andromeda, is about 2.5 million light-years. And between our galaxy and Andromeda, the space is almost unfathomably empty. Intergalactic space has a density of roughly 1 atom per cubic meter. Not per cubic centimeter, per cubic meter. That is 1,000,000 times emptier than the space between stars, which was already unimaginably empty compared to everyday experience. If you were somehow placed in intergalactic space, far from any galaxy, what would you experience? Darkness, complete, total darkness. No star would be visible to your naked eye. The nearest galaxy would be a faint smudge if you could see it at all. The temperature around you would be approximately 2.7 Kelvin, just barely above absolute zero, heated only by the faint cosmic microwave background radiation left over from the Big Bang. You would be surrounded by nothing in every direction for millions of light years. No matter, no energy, no light, no warmth, no hope of rescue. Just an eternal, frozen void stretching in every direction beyond comprehension. But even intergalactic space is not the emptiest place in the universe. Because the universe has structure. Galaxies are not distributed randomly. They are arranged in a pattern called the cosmic web. Imagine a three-dimensional network of filaments, like a spider's web stretched through all of space. Galaxies cluster along these filaments and at the nodes where filaments intersect. But between the filaments, filling the vast majority of the universe's volume, are cosmic voids. Regions of space that are even emptier than intergalactic space. Regions where almost nothing exists at all. The first major cosmic void was discovered in 1981 when astronomer Robert Kirshner and his colleagues were conducting a survey of galaxies in the direction of the constellation Bootes. They found something unexpected. A region of space roughly 330 million light-years across that contained almost no galaxies. Where there should have been thousands of galaxies, there were only about 60. This became known as the Bootes void. 330 million light-years of almost pure emptiness. Let me put that in perspective. Light takes 330 million years to cross this void. It has been expanding and growing emptier since the early ages of the universe. If Earth were located at the center of the Bootes void, instead of in the Milky Way, our understanding of the universe would be profoundly different. We would look out in every direction and see almost nothing. No nearby galaxies, no Andromeda getting closer. Just darkness. Until telescopes became powerful enough in the mid-20th century. We would not have known that other galaxies even existed. We might have spent our entire history believing that our Milky Way was the only galaxy in existence, alone in an infinite void. The accident of our position in the cosmic web has shaped our entire understanding of reality. And the Bootes void is not even the largest empty region we know of. In the direction of the constellation Eridanus, there is a feature known as the CMB cold spot, a region of the cosmic microwave background that is slightly colder than its surroundings. One explanation for this cold spot is a supervoid, possibly up to 1.8 billion light-years across, containing far less matter than average. If confirmed at that scale, this would be one of the largest structures, or rather one of the largest absences of structure in the observable universe. And here is a fact that might make you feel uncomfortable. There is evidence that our own Milky Way galaxy might be located inside a cosmic void, not one as extreme as the Boots void, but a region of below-average density called the KBC void, possibly 600 to 2,000 million light-years across. We might be living inside a cosmic void right now and never notice, because from the inside, you simply see fewer galaxies in certain directions than you might otherwise expect. Let me now share something about the cosmic web structure that reveals just how dominant emptiness is in our universe. Scientists have mapped millions of galaxies and measured the large-scale structure of the cosmos. What they find is that the cosmic web, the filaments and walls and clusters where galaxies live, occupies only a small fraction of the universe's total volume. Cosmic voids, the empty regions between filaments, occupy roughly 60 to 80% of the total volume of the universe. Let that register. Up to 80% of the volume of the entire observable universe is void. Empty regions with almost nothing in them. The galaxies, the stars, the planets, everything you can see, everything you know, is squeezed into a thin webwork that fills perhaps 20 to 40% of cosmic volume. We do not live in a universe of stuff. We live in a universe of void with thin threads of matter strung through it. Now I need to tell you about the most shocking aspect of cosmic emptiness. Because everything we have talked about so far, the atoms, the stars, the galaxies, the cosmic web, all of that is just the matter and energy we can see. The matter we know about. The ordinary matter made of protons, neutrons, and electrons. And it turns out that ordinary matter, everything that you and I are made of, everything that stars and planets are made of, everything that telescopes can detect directly, makes up only about 5% of the total stuff in the universe. 5%. 95% of the universe is something else entirely. Something we cannot see. Something we barely understand. And this brings us to two of the greatest mysteries in all of science: dark matter and dark energy. Let me tell you the story of dark matter. It begins in 1933 with a brilliant but cantankerous Swiss-American astronomer named Fritz Zwicky. Zwicky was studying a large collection of galaxies called the Coma Cluster, about 320 million light-years from Earth. He was measuring how fast the individual galaxies within this cluster were moving. Using their speeds, he could calculate how much total mass the cluster must contain to hold itself together gravitationally. It is like measuring how fast cars go around a curve and calculating how much friction the road must be providing. The faster the cars, the more friction needed. Similarly, the faster the galaxies, the more mass needed to keep them bound in the cluster. When Zwicky did this calculation, he got a shocking result. The galaxies were moving far too fast. Based on the visible matter he could see, the luminous galaxies and gas, the cluster did not have nearly enough mass to hold together. The galaxies should be flying apart, escaping the cluster's gravitational pull. But they were not flying apart. They were staying together. Something unseen was providing additional gravitational pull. A lot of additional gravitational pull. Zwicky calculated that the cluster must contain about 400 times more mass than what was visible. He called this missing mass dark matter, or Dunkel Materie in German. And then, for nearly 40 years, the scientific community largely ignored him. Zwicky was known for being difficult to work with, and his claims seemed too extraordinary. Surely there was some error in his measurements or his calculations. It was not until the 1970s that dark matter came roaring back into the scientific conversation, thanks to the meticulous work of astronomer Vera Rubin and her collaborator Kent Ford. Rubin was studying how fast stars orbit within individual galaxies. She focused on the Andromeda galaxy and others, measuring the rotational speed of stars at different distances from the galactic center. Now, based on what we understand about gravity, stars further from the center of a galaxy should orbit more slowly than stars closer in. This is exactly what we see in our solar system. Mercury, close to the Sun, orbits quickly. Neptune, far from the Sun, orbits slowly. This makes sense, because almost all the mass of the solar system is concentrated in the Sun at the center. Rubin expected to see the same pattern in galaxies. Stars far from the bright central region should orbit more slowly because they are further from where most of the visible mass is concentrated. But that is not what she found. Instead, she discovered that stars at the edges of galaxies orbit at roughly the same speed as stars much closer to the center. The rotation curves were flat. They did not decrease with distance. This was extraordinary. It meant that the mass of the galaxy was not concentrated in the center where the visible stars were. It meant there must be an enormous amount of additional, invisible mass extending far beyond the visible edge of the galaxy. A vast halo of unseen material, far more massive than the galaxy itself, extending in every direction. Rubin published her results starting around 1970 in papers in the Astrophysical Journal, and unlike Zwicky's earlier work, this time the data was so clear, so meticulous, and so reproducible that it could not be ignored. Galaxy after galaxy showed the same pattern: flat rotation curves. Too much speed for the visible mass. Dark matter was everywhere. And now, half a century later, we know a great deal about dark matter, even though we still do not know what it actually is. We know it makes up roughly 27% of the total mass energy of the universe. We know it does not interact with light, which means it does not emit, absorb, or reflect electromagnetic radiation of any kind. This is why we cannot see it. Telescopes are useless for directly detecting dark matter because it is completely invisible to every form of light, from radio waves to gamma rays. We know it does not interact via the strong nuclear force, which is the force that holds atomic nuclei together. We know it does interact via gravity, because that is how we detect its presence, through its gravitational effects on visible matter and light. There is also some possibility that it interacts through the weak nuclear force, which is why some candidates for dark matter particles are called WIMPs, weakly interacting massive particles. We know that dark matter forms a vast cosmic scaffold, a web-like structure throughout the universe, and that ordinary matter, the stuff galaxies are made of, accumulated along this scaffold like dew forming on a spider's web. Without dark matter, galaxies as we know them would not exist. Stars would not have formed in the way they did. You and I would not be here. This invisible nothing is the reason something exists. Perhaps the most dramatic evidence for dark matter comes from an event called the Bullet Cluster, observed in detail by the Chandra X-ray Observatory. The Bullet Cluster is actually two galaxy clusters that collided with each other. When the clusters collided, the regular matter, mostly hot gas, interacted with itself and slowed down. You can see this gas through X-ray observations, and it is concentrated in the central collision region. But when astronomers used gravitational lensing, using the bending of light from background galaxies to map where the mass actually is, they found that most of the mass had passed right through the collision without slowing down. The dark matter halos of the two clusters went right through each other, because dark matter does not interact with itself or with normal matter except through gravity. This beautiful observation shows the visible matter and the dark matter separated from each other during the collision, providing powerful direct evidence that dark matter is a real substance and not just a modification of our gravity equations. Here is something to think about that makes this all feel immediate and personal. Dark matter is not just out there in galaxies and clusters. It is here. It is around you, right now. Our own Milky Way galaxy has a dark matter halo, and we orbit through it as the Earth moves through the galaxy. Scientists estimate that millions of dark matter particles pass through your body every single second. Right now, as you watch this video, unknown particles of unknown nature are streaming through your flesh, through your bones, through the very atoms of your brain, and you cannot feel them, cannot see them, cannot detect them with any technology we currently possess. You are continuously bathed in an invisible river of unknown matter, and you are completely oblivious to it. 85% of all the matter in the universe is this invisible, unknown substance. We are a minority. We are the anomaly. Normal matter, the stuff of stars and planets and people, is the rare exception. Dark matter is the norm. We are the weird ones in this universe. But dark matter, for all its strangeness, is not even the biggest component of cosmic nothingness. That title belongs to dark energy. And dark energy is even more mysterious, even more terrifying, and even more dominant than dark matter. Let me tell you how it was discovered. In 1998, two independent teams of astronomers were studying a particular type of exploding star called a Type 1a supernova. These supernovae are useful because they all explode with roughly the same intrinsic brightness. This makes them what astronomers call standard candles. By measuring how bright a Type 1 supernova appears to us, and comparing that to how bright we know it actually is, we can calculate how far away it is. And by measuring the redshift of the supernova's host galaxy, we can measure how fast it is moving away from us. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were using these supernovae to measure something specific. They wanted to know how fast the expansion of the universe was slowing down. Because at that time, everyone assumed the expansion was slowing. After the Big Bang, the universe started expanding. But gravity pulls matter together. So gravity should be acting like a brake, gradually slowing the expansion over time. The only question was how much it was slowing. But when the data came in, both teams independently found something that nobody expected. The distant supernovae were dimmer than they should have been. This meant they were further away than predicted. And the only way to explain this was if the expansion of the universe was not slowing down at all. It was speeding up. The universe's expansion is accelerating. Something is pushing the universe apart, overcoming gravity on the largest scales, causing galaxies to fly away from each other faster and faster over time. This unknown something was named dark energy, and it earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics. What is dark energy? Honestly, we do not know. It makes up approximately 68% of the total mass energy content of the universe. Combined with dark matter's 27%, that means 95% of the universe is stuff we cannot see and do not understand. Dark energy appears to be a property of space itself. Every cubic meter of empty space contains a certain amount of dark energy, and as the universe expands and more space is created, more dark energy comes into existence. Unlike matter and radiation, which get diluted as the universe expands, dark energy maintains a constant density. More space means more dark energy, period. This makes dark energy's influence grow over time. In the early universe, when everything was close together and dense, dark energy was a minor player. Matter and radiation dominated. But as the universe expanded and matter spread out, dark energy's constant density eventually won out over the decreasing density of matter. About 5 billion years ago, dark energy became the dominant component of the universe. And ever since, the expansion has been accelerating. One possible explanation for dark energy connects back to our earlier discussion of vacuum energy. Remember, quantum field theory tells us that empty space has energy. Fluctuations in quantum fields give the vacuum a non-zero energy density. Some physicists propose that dark energy is simply the vacuum energy of quantum fields, what Einstein called the cosmological constant, the energy of nothingness itself, pushing the universe apart. But as we discussed, the predicted value of vacuum energy from quantum field theory is absurdly larger than what we observe, off by 122 orders of magnitude. So while vacuum energy might be the right general concept, something is profoundly wrong with our calculation of it. Another possibility is something called quintessence, a hypothetical scalar field that pervades all of space and whose energy changes over time. Unlike a cosmological constant which is fixed, quintessence could vary, leading to different expansion rates at different epochs. But so far, observations are consistent with a simple cosmological constant, and quintessence remains speculative. The honest answer is that we are largely in the dark about dark energy. We know it exists, we can measure its effects, but we do not understand its nature at any fundamental level. Let me tell you what makes dark energy truly terrifying. Its implications for the future of the universe are stark. If dark energy continues to drive accelerating expansion, as it appears to be doing, then the fate of our universe is a slow, inexorable dissolution into nothingness. Here is what happens. As the expansion accelerates, galaxies that are currently visible to us will gradually be pushed beyond our cosmic horizon. They will be carried away by the expansion of space faster than their light can reach us. They will redshift out of visibility and vanish. From our perspective, they will simply disappear. In the far future, any civilization living in our galaxy's local group will look out into the cosmos and see nothing. No other galaxies. No evidence that a universe of billions of galaxies ever existed. They will be stranded on a cosmic island, surrounded by pure void, with no way of knowing that the universe was ever different. All evidence of the wider cosmos will have been erased by expansion. If dark energy's strength increases over time, which is possible though not currently supported by evidence, then the situation becomes even more extreme. In a scenario called the Big Rip, the accelerating expansion eventually becomes strong enough to tear apart galaxy clusters, then galaxies themselves, then solar systems, then planets, then molecules, then atoms, and ultimately, space-time itself. Everything rips apart into nothing. The universe literally tears itself to pieces. Even if dark energy remains constant, as current evidence suggests, the long-term future is what physicists call the heat death. Stars burn out. Stellar remnants cool. Black holes slowly evaporate through Hawking radiation. Over timescales so vast, they make the current age of the universe seem like the blink of an eye. Everything dissipates. In approximately 10 to the power of 100 years, the last black holes will have evaporated. What remains is a universe of stray photons, neutrinos, and possibly electrons and positrons, spread so thinly through an incomprehensibly vast space that no two particles will ever interact again. No structure, no complexity, no possibility of life or thought or meaning. Just an infinite, cold, dark, expanding nothing. Forever, this is where the universe is heading. The nothing will win. Not today, not for an inconceivable amount of time. But ultimately, the emptiness that dominates the universe at every scale, from atoms to galaxies to cosmic voids, will become total. The brief flash of complexity that includes stars and planets and people is just that. A brief flash, a temporary eddy of organization in an ocean of nothingness that is slowly, inevitably smoothing itself out.